Hey, we're talking about logic today, and it may not seem like it has anything to do with geometry, but we'll make the connection soon enough. Trust me. We're talking about conditional statements today. I'm sure you're familiar with compound statements. You learned that in English a long time ago. Compound statement might be something like, I am awake and I am heading to school, right? Two complete statements that stand on their own, joined by something like the word and or the word or some other possibilities. So a conditional statement is two complete statements that stand on their own, joined not just by a word in between, but by the words if and then. So here's the form of a conditional statement right here. It always starts with the word if. Okay? And then that's followed by a complete statement. Then comes the word then, followed by another complete statement that could stand on its own. The statement that follows the word if is called the condition of the conditional statement, or it is also referred to as the hypothesis of the conditional statement. And the statement that follows the word then is called the conclusion of the conditional statement. I got to talk about this word hypothesis because this word hypothesis means something different from what you have learned in the past. And it's not that you learned wrong, it's just that hypothesis in a science classroom means something different from the word hypothesis in a math classroom or in a logic classroom. And you know what it means in science, I'm sure. Hypothesis is that thing that you write out at the beginning of your lab write up after you've done an experiment saying, this is what we think we're going to discover when we do this experiment. Here's what we think might be true. And then you write up what you did in the experiment, and at the end, in your conclusion, you write out whether you actually found that thing to be true or not. Okay? But in math, the words hypothesis and conclusion mean different things. Hypothesis, you need to think of hypothesis in this context as something that we already know to be true. It will really help if you think of it that way. Something that we already know is true, already. Okay? We don't have to investigate. We already know it. And the conclusion is not really a commentary on the hypothesis like it is in science. Again, in a science lab, in your conclusion, you return to the hypothesis and comment on it and say, well, we found out that it is true. Or, no, we found out that it's not really true. Or we have no idea because our lab went so badly. But in mathematics, the conclusion is not a commentary on the hypothesis. The conclusion is a whole completely different new statement that is guaranteed to be true because the hypothesis is true. Okay? And we'll look at some mathematical statements like this at the end of this lesson. But let's start with some English sentences that may or may not be true. We don't really care. For instance, this conditional statement right here. If elephants eat, then antelopes advance. So what I've underlined there, elephants eat, that is a complete statement on its own. It stands on its own. It's a complete English sentence. Elephants eat. Okay. Or we could say elephants do eat. We'd be saying exactly the same thing, just a slightly different way of wording it in our language. Okay. Antelopes advance is a complete statement. Joined together with the words if and then, it's a conditional statement. Okay. Now, just as we have variables and symbols, all kinds of symbols in algebra to translate English sentences into algebraic statements, we do the same in logic, but we have different kinds of symbols. For instance, if I said, my age is the same as your age, and we wrote that out as an English sentence, my age is the same as your age, and I wanted to represent that algebraically with some variables and symbols, I might choose the variable m to stand for my age, and then the symbol equals for is the same as, and then the letter y or variable y for your age, right? And m and y would be smart choices for those variables, because if I used the letter a for my age, and then I got to your age and I'm thinking age, okay, well, that's pretty much a pointless sentence to write. I mean, what does that communicate to you that you didn't already know, right? Nothing. So the choice of variables can be helpful. So I want to choose a variable, not to stand for a number or a value, but this whole statement, elephants eat. Okay? And since both words begin with the letter E, I'm going to choose the variable E to stand for that complete statement, elephants eat. I'm going to choose the letter A to stand for the complete statement, antelopes advance. And then the words if and then, the two of them get translated into this one symbol here, the arrow pointing from the E to the A. It must go from the E to the A, not the other way around. And we always write our arrows going from left to right in logic. We always do it that way. Okay? So if we're reading this logical statement out loud, this is how we read it. Careful, here comes another word you need to pay attention to, because I'm going to use it a lot. E implies A. If I'm reading this logical symbol out loud, I'm not going to say E arrow A or E arrows A. That sounds like you never learned this stuff. Okay, that would be like somebody reading this, and if I asked you, hey, would you read this algebraic sentence here for me? And you said M//Y or M two horizontal lines Y. Okay, the word for this is equals, and you know it, and that's what you would say. The word for this arrow is implies. E implies A. But again, the word implies means something different in mathematics than it does in everyday conversation. If I tell you, my friend implied that he bought me a gift, well, what I'm telling you is he didn't really come out and say he bought me a gift. He said some stuff to make me think that he bought me a gift, but he didn't come right out and say it. He just implied it, trying to lead me to believe without coming out and saying it. And then later, if he didn't buy me a gift, he can say, well, I never said that, right? But in mathematics, when we say E implies A, we mean that E guarantees the conclusion A. It is absolutely, certainly going to lead to the conclusion A. Another way to read this out loud would be to say, if E, then A. Right? So we have those two ways of reading this out loud. If E, then A. Sorry, that E kind of got lost in there. If E, then A, or we could say E implies A. Please don't say E arrow A, okay? All right. Now, we're going to learn how to write what we call the converse of a conditional statement. Okay? And I'm just going to get right into it. We write the converse of a conditional statement by swapping the condition and the conclusion. You leave the arrow right where it is. It points in the same direction always from left to right. But we swap places with the condition and the conclusion. So now it's A implies E, or if A, then E. Okay? The inverse of a conditional statement is found by doing what I'm going to call negating the conditional statement. I want a word that I think communicates or explains what it is that you do, but I got to be careful about this word negate, because in logic we don't really talk about the negative of something like we do in numbers or in algebra. If I said, what is the negative of 6, you'd write -6. If I asked you what's the negative of -6, you would say 6. We don't talk about negatives in logic. We do talk about opposites. Okay. And we use that for numbers also. If I said, what's the opposite of -6, you'd say 6. We do talk about opposites, but not really negatives, and we don't have a negative symbol in logic. Okay? So when I say negate both parts of the conditional statement, here's how we write it. It looks like a squiggly E implies squiggly A. Okay? But we don't say squiggly, and we don't say negative. It's not a negative symbol. Okay? It's a not symbol. N-O-T, not. We read this not E implies not A. All right? That's what I mean by negating both parts of the original conditional statement. And then the contrapositive of the original conditional statement is created by doing both of these things, swapping and negating of the original conditional statement. So okay, the A is going to come from the back to the front, trade places with the E, but we're also going to take the opposite of A. So not A. And the E is going to move to the conclusion part of this sentence, but we're also going to take the opposite of that, not E. There's the contrapositive of the original statement. Okay. Now, converse is not a thing by itself. Okay. Just like opposite is not a thing by itself. Here's what I mean. Forget about the logic for a second. Let's go back to numbers. I'm going to ask you a nonsensical question about these two numbers. You ready? There's no good answer for this question because the question doesn't make any sense. I'm telling you right up front. Between the 6 and the -6, which one of those numbers is the opposite? Doesn't make any sense, right? When you say the opposite, what must follow that phrase is of what? Opposite really is not a thing, it's a relationship with something else. 6 is the opposite of -6, and -6 is the opposite of 6. They are opposites of each other. Okay? So this statement here, E implies A, and this statement here, A implies E, they are converses of each other. It's not that one of them is the statement and the other one is the converse. Same between this statement and this one. They are inverses of each other. Okay? An inverse statement does not have to have those not symbols in it. Okay? I mean, we could say, let's start our conversation with this sentence right here. Not A implies not A. And then I could say, what is the inverse of that statement? Okay. And the inverse of that statement would be this one. E implies A. You would not say to me, whoa, it already is an inverse. No. Okay. Just as if I asked you, what is the opposite of -6? You wouldn't say to me, what are you talking about, Mr. Rutillo? It's already an opposite. Well, yeah, okay, it is, but it has an opposite also, right? You get my point here? Likewise, the contrapositive of the original statement, those two statements are contrapositives of each other. Okay? And finally, before we go on to another example, let's talk about retranslating these these logical statements here, these new logical statements that I've created back into English, because you're going to have to do this kind of thing. I'm going to ask you to do it on the homework, quizzes, test. A implies E. How would that read in English? If, always start with if, okay? And the A stands for antelopes advance. Antelopes advance. Comma. Then the arrow becomes the word then. E stood for elephants eat. Okay. So I went from this original English sentence, I translated it into logical symbols. I took the converse of that logical statement, and then I retranslated that converse back into English. Okay. How about not E implies not A? What does not elephants eat? If not elephants eat, that's a little bit awkward in English, isn't it? If not elephants eat, I'm sure you can think of a better way to phrase that. How about if elephants don't eat, right? Because the equivalent of elephants eat is elephants do eat. That means exactly the same thing in English, right? So the opposite of elephants do eat would be if elephants don't eat. Elephants don't eat. Then, and not A would be antelopes don't advance. Okay. There are other ways that you could phrase these things in English that would make as much sense, but might require a lot more words. Like, for instance, instead of saying if elephants don't eat, you could say if it is not the case that elephants eat, or if it is not true that elephants eat. There's a lot more words to say what I think is most simply said by elephants don't eat and antelopes don't advance. If I had an English sentence that said this is green, the opposite of that would be this isn't green. Or if this was late, this wasn't late would be the opposite. Okay. And finally, the contrapositive, not a, or if antelopes don't advance, then not e, elephants don't eat. Elephants don't eat. Okay? All right. Let's go down to another example. As I said earlier, an inverse does not have to have not symbols in it. A conditional statement can have a not symbol in it to begin with, like in this example here. Here's a conditional statement that has a not symbol in it to begin with. Because the English sentence that this is coming from is if it is not raining, then we're swimming. Hey, if it's not raining today, we're going to be swimming. Okay? That's the kind of thing you might say or think. Right? So when I want to choose a variable to stand for it is not raining, I'm not going to choose the variable r to stand for it's not raining. That would be a little confusing. Okay. I'm going to think of r as standing for it is raining. That's what I'm going to think of r standing for. It is raining. So then to write it is not raining in symbols, I'll write not r. Okay. I strongly recommend that you make similar kinds of choices. I mean, in algebra, if we want to choose a variable to stand for a negative number, we'll probably just choose a variable like x. We'll say, well, x is equal to -6. Why not? X could be a negative number. Okay. You could also say, well, I want -x to be equal to -6. And then x would be equal to +6. You could make that choice too. Right? Most people probably wouldn't do that. They would probably just choose x to stand for the negative. But in logic, I think you're asking for trouble if you use a plain old variable to stand for like a not kind of a sentence. Okay? So I'm choosing not r to stand for not raining and then s to stand for swimming. Pause this video and take a minute and see if you can come up with just the logical converse, inverse, and contrapositive. Not even the English, just right here based on these prescriptions of how to get those sentences. Pause the video right now. Okay, did you try these? Converse is swapping, right? Swapping these two things, the S and the not R. So the S comes up front and the not R goes back. Yes, the not moves with the R. Okay. So that's the converse of the original statement. The inverse is found by negating both parts of this statement. What is the opposite of not R? Well, it's R, just like the opposite of -6 is +6. And then what is the opposite of S? Well, it's not S. And then the contrapositive, you swap and negate both parts. So the S comes up front and we take the opposite, not S. The not R moves to the back, and we take the opposite of not R, which is R. Okay. And you know what? I'm not going to take the time in the video to go through the retranslating back into English of all of these things. I will finish that out and post it in the completed version of these notes, but I'm not going to take the time in the video to do it because I think you can probably do it. Okay. But again, when you're applying the rules of writing converses, inverse, and contrapositives, a negative moves with the variable if you're swapping it. Okay. All right, now let's take a look at some mathematical statements that are conditional statements. This first one here, if two angles are vertical angles, then they are congruent. Now that's something we learned a while back, and we proved that it is true. Guaranteed. If two angles are vertical angles, then they are absolutely congruent. You know, these English sentences up here, we could debate about whether they're true or not. And they might be true one day and then not true another day. But in mathematics, if two angles are vertical angles, guaranteed those angles are congruent. Okay. And so again, we might use the word implies, but we mean guarantees. Vertical angles implies congruent angles. Okay. I'm using V to stand for angles are vertical angles. I'm using C to stand for those angles are congruent. Okay. The converse then, we're going to swap. Swap the C and the V. The inverse, we're going to take the opposite of the V and the C. So not V implies not C. And the contrapositive, we're going to do both. We're going to swap and negate. So put the C in front, but take the opposite. Put the V at the end, but take the opposite. Okay. Let's go through this mathematical statement over here. If an angle's measure is 90 degrees, and I'm using the letter N to stand for an angle's measure is 90 degrees, okay, then it, meaning the angle, is a right angle. And I'm using the letter R to stand for it is a right angle. That whole statement. Okay. What's the converse? You get the converse by swapping. R implies N. You get the inverse by negating both parts. The opposite of N, or not N, implies not R. And then the contrapositive is found by swapping and negating. So take the R, put it in front, and take the opposite. Take the N, put it at the end, and also take the opposite. Okay. Now this is also a true statement here. If an angle's measure is 90 degrees, guaranteed it's a right angle, right? Let's consider whether or not the converse, the inverse, or the contrapositive, if any of these statements are also true. Okay. If an angle is a right angle, does that guarantee that its measure is 90 degrees? If I tell you I got a diagram that I'm not showing you, and I'm looking at a certain angle and I'm telling you it's a right angle, when I reveal the diagram to you, are you going to be surprised that it's 90 degrees? No, you're not going to be surprised. That's absolutely guaranteed to be true. If I tell you an angle is a right angle, its measure is 90 degrees. What about the inverse? If an angle's measure is not 90 degrees, if I tell you that diagram that I have hidden from you, I'm looking at an angle and its measure is not 90 degrees, can you conclude with absolute certainty, well, then it must not be a right angle? Yeah, you bet you can. Okay. And how about if I say the diagram that I'm hiding, I'm looking at an angle and it is not a right angle? I already know it. Okay, this is the hypothesis in this, but again, we're acting as if the hypothesis is something we already know. I'm looking at this diagram, I'm looking at an angle, and I'm telling you it's not a right angle. Can you tell me for sure, well, then it's not 90 degrees? You bet you can. Okay. So in this case, which is a foreshadowing of what we're going to look at next, in this case, when we have a conditional statement that is true, it turns out that the converse of that original statement is also true, and so is the inverse of that original statement also true, and so is the contrapositive of the original statement also true. Here's the trouble that people get into logically in their lives, is they believe, because they haven't been taught, that you can't always do that. If you have a conditional statement that is true, you can't guarantee me that the converse is also going to be true. You can't guarantee me that the inverse is also going to be true. And here is a set of examples where I can demonstrate that for you. If two angles are vertical angles, then they are congruent. We know that that's true. What about the converse of that statement? If I told you I got a diagram that's hidden from view from you, and I'm looking at two angles and they are congruent, I'm telling you, I'm looking at them. You can't see them, but trust me, they are congruent. Can you know for sure that they are vertical angles in my diagram? No, you can't be sure of that. I could have two congruent angles in my diagram that are very, very far away from each other, that are not directly across from each other like that. So this is a false statement. The original statement was true, but the converse of it is not guaranteed to be true. What about the inverse? If two angles in the diagram that I'm hiding from your view, and I'm saying they're not vertical angles, trust me. I'm looking at this angle 1 and this angle 2, and they're not vertical angles, trust me. Can you guarantee that they're not congruent? That's what the inverse is saying. If two angles are not vertical angles, then they are not congruent? No, they might be congruent, right? I mean, just because they're not vertical angles. So what? I mean, they're not vertical angles. That means they're far away from each other. They're not connected to each other. They might still be congruent. This is a false statement. Now, what about the contrapositive? Is that going to be true? I mean, again, the original statement is absolutely true. If two angles are vertical angles, then they are congruent. What if I tell you, yeah, I'm looking at two angles in my picture that you can't see, and those two angles are not congruent to each other? I know you can't see them, but trust me, I'm not lying. I'm not playing a game with you. Trust me. They are not, I'm looking at angle 1 and angle 2, and they're not congruent to each other. Can you conclude that they are not vertical angles? Well, you're probably right. Yes, you absolutely can conclude that they are not vertical angles. If I tell you they're not congruent, how could they be vertical angles, right? Because if they were vertical angles, they would be congruent, right? This is that contrapositive reasoning that you all have known how to do for a long time in your life. I'm not teaching you something here that you don't know. If you're my students, you remember the story I told you about my daughter Kristen when she was 5 years old, about the peas and the cup, and how she knew how to do this contrapositive reasoning when she was 5. Not because she was the most brilliant 5-year-old in the world, but just because when your brain matures to a certain point, you understand this, right? The contrapositive of a conditional statement is always as equally true as the original statement. We say it is logically equivalent to the original statement, or it means the same thing, or it communicates the exact same information as the original statement. Nothing new, nothing different. And I have tried to highlight this fact for you at the bottom of this page in every way I could think of. I bold-faced it, I put a star in front of it, I highlighted it, and I put a box around it. Only the contrapositive of a logical statement is logically equivalent to the original statement. You have to know that in the next lesson for the homework I'm going to be asking you to do. And you have to know how to write a contrapositive of a statement. Converse and the inverse are things I do want you to know how to write. They're not going to be nearly as important to us. We're not going to use them nearly as much as contrapositives in the next lesson. So that's a really, really important fact. Okay? All right. Get after the homework.